The interstellar object known as 3I/Atlas has quickly become one of the most captivating subjects in modern astronomy, precisely because scientists cannot rely on familiar expectations when studying something that originated beyond our solar system. Every time researchers turn their telescopes toward it, they are met with new data that challenge assumptions and expand the boundaries of what we understand about the composition and behavior of interstellar visitors. Since this is only the third confirmed object from another star system to enter ours, following the enigmatic 1I/Oumuamua in 2017 and the more traditional comet-like 2I/Borisov in 2019, each observation provides a rare and invaluable glimpse into the broader cosmic environment that surrounds our Sun. The discovery of 3I/Atlas in early July immediately sparked intense curiosity, especially because it appeared to approach from far beyond the solar system at a remarkable velocity, hinting at a long and ancient journey through interstellar space. Multiple major observatories, including NASA's Hubble Space Telescope, the James Webb Space Telescope, SPHERE-X, and the Transiting Exoplanet Survey Satellite TESS, quickly focused their instruments on the object. Together, these telescopes form an exceptionally powerful observational toolkit, capable of detecting subtle chemical signatures, faint variations in brightness, and the finest structural details of distant cosmic entities. Even with the combined observational power of these instruments, the more astronomers analyzed 3I/Atlas, the more puzzling and extraordinary it appeared. While experts generally agree that the object behaves like a comet, meaning a body composed mostly of ice and dust that releases gas as it approaches the Sun, the emerging data reveal that it diverges from typical cometary behavior in several fundamental ways. Rather than fitting neatly into established comet classifications, 3I/Atlas appears to represent something far stranger, an object shaped by processes or environments that we have little experience with inside our own solar system. One of the most surprising findings comes from SPHERE-X and the James Webb Space Telescope, both of which identified an unusually high ratio of carbon dioxide to water in the object's coma. In comets, the coma is the diffuse envelope of gas and dust that forms as sunlight heats the icy nucleus, causing volatile substances to sublimate and stream outward. Most comets from our solar system contain water ice as the dominant volatile component, with smaller amounts of carbon dioxide and carbon monoxide mixed in. 3I/Atlas, however, defies this trend by containing the highest carbon dioxide to water ratio ever recorded in a comet-like object. This suggests either a fundamentally different formation environment or a history of exposure to extreme radiation conditions that altered its chemical composition in ways rarely seen before. If this object formed near the carbon dioxide ice line in its home star system, a region where CO2 freezes more readily than water, its composition might reflect a completely different type of planetary nursery than the one that formed Earth and its neighbors. Even before its official discovery in July, the TESS spacecraft had unknowingly captured images of the object months earlier. These archive detections revealed that 3I/Atlas was already surprisingly bright and active at a distance of 6 astronomical units from the Sun, a region far beyond Jupiter's orbit. Most comets begin displaying noticeable activity only when they approach much closer to the Sun, typically around 3 astronomical units or less. The early activity of 3I/Atlas at such great distances implies that its volatile materials require far less heat to sublimate, another indicator that its composition is unlike that of the comets we are familiar with. This unusual behavior also suggests that the object may contain exotic ices or compounds that react more sensitively to sunlight, further reinforcing the idea that it formed in a very different environment. The Hubble Space Telescope added yet another layer of intrigue with its high-resolution imaging. Instead of displaying a classic comet tail, a long, bright streak of dust and gas trailing behind the nucleus, Hubble revealed a teardrop-shaped cocoon of dust enveloping the object. This dense, uneven cloud of material seems to cling closely to the nucleus, giving the object a distinctly asymmetric appearance. The lack of a well-defined tail is highly unusual for an active comet and raises questions about the mechanics of how material is being released and distributed around the nucleus. Harvard astronomer Avi Loeb has speculated about unconventional explanations, even suggesting that the strange morphology and extreme chemical composition might allow room for speculation about artificial origins. While most scientists remain cautious and grounded in natural explanations, they acknowledge that 3I/Atlas is far from ordinary. The origin of this interstellar traveler remains one of the most difficult mysteries to unravel. In a recently published preprint, a team of international researchers proposed two primary possibilities. The first is that the object's ices were subjected to far more radiation than typical comets in our solar system, perhaps due to spending millions or billions of years drifting through regions of interstellar space filled with energetic particles and cosmic rays. Over such long periods, these processes could break down water molecules, liberate carbon dioxide, or restructure the object's surface layers in unexpected ways. The second hypothesis is that 3I/Atlas formed closer to the CO2 ice line in its parent protoplanetary disk than comets in our own solar system typically do. If true, the object's composition would offer a rare window into how chemical distributions vary across different planetary systems, helping scientists refine models of planet formation in environments beyond our sun. Despite the substantial amount of data collected so far, researchers recognize that much more analysis and peer review are required before drawing solid conclusions. Interstellar objects are inherently difficult to study, not only because they move quickly and appear only briefly, but also because they offer only tiny observational windows before they vanish back into the depths of space. 3I/Atlas is currently on a trajectory that carries it through the inner solar system before ejecting it once again into interstellar space. As it continues its outbound journey, it will make relatively close passes by Venus, Mars, and Jupiter, presenting unique opportunities for additional observations. Harvard astronomer Avi Loeb has proposed that NASA's Mars Reconnaissance Orbiter could attempt to capture detailed images or spectral data as the object passes within less than 2 million miles of the red planet. A close-range observation like this could yield information far more detailed than anything obtained from Earth-based or orbital telescopes. About 5 months after the Mars encounter, NASA's Juno spacecraft, currently orbiting Jupiter, may have a chance to intercept or observe 3I/Atlas as it passes near the gas giant. If mission controllers can adjust Juno's orbit or observational schedule in time, the spacecraft might be able to capture unprecedented close-up data on the object structure, rotation, and composition. Such an opportunity would be exceedingly rare, as spacecraft encounters with interstellar visitors are almost impossible to plan in advance. A successful observation by Juno could dramatically improve our understanding of how this object compares to other comets, and could reveal entirely new categories of interstellar materials or physical processes. Ultimately, 3I/Atlas serves as a powerful reminder that our solar system is not isolated. Objects from distant star systems occasionally wander into our cosmic neighborhood, carrying with them chemical fingerprints, physical structures, and histories shaped by environments beyond anything humans have directly observed. Each interstellar visitor offers a chance to broaden our understanding of planetary formation, chemical evolution, and the diversity of conditions across the galaxy. Whether 3I/Atlas turns out to be a natural but exotic comet, a fragment of a disrupted exoplanetary body, or something even more unusual, it is certain to reshape scientific discussions for years to come. The scientific community eagerly awaits the results of ongoing and future observations, recognizing that this fleeting encounter may offer insights that cannot be replicated for decades or even centuries. As 3I/Atlas accelerates toward its outbound path, leaving behind the sun's gravitational influence, astronomers around the world are focused on extracting as much knowledge as possible before it disappears into the vast darkness of interstellar space. Its strange chemistry, unexpected brightness, unusual dust structure, and mysterious origins ensure that it will remain one of the most studied and debated cosmic visitors in modern history. It may take years of analysis and future discoveries to fully understand what this object represents, but its brief visit has already expanded our understanding of what is possible in the universe.